right, are there any questions? Okay.
On the practice system, for number 5, it says when ozone undergoes a unimolecular collision, the most likely products are, and it gives some examples or choices, but when a molecule goes under a unimolecular collision, does it all have to be separated, or is it the one that's most stable?
Unimolecular collision doesn't have to, it doesn't have to separate. I mean, different things can happen. For example, if this collides with the wall or some inert molecule, it can go to an excited state, where the electron gets promoted to higher energy. So that's possible, but it depends on how much energy is in that collision. So it could be enough to bump up the electron, or it could be enough to break the bond. Now, ozone has fairly weak bonds. The oxygen-oxygen bond in there can easily dissociate. And so unimolecular collision can actually go through like a path like this, or it can just go and break apart. But when it breaks apart, it wants to break apart, it just doesn't break apart. It wants to break apart into things that are reasonably stable, if possible. So if it breaks up into 3 atomic oxygens, it's doesn't look good.
So it will make more sense if it's,
maybe 2 minus, 2 plus, and a 0. Does that look very good? No. And so we're always looking for things that look stable, and so you look for something that looks reasonably stable.
So maybe like O2 minus plus O2?
O2 minus plus O2 is not stable at all, because this...
Oh no, I meant O like 2 minus on the top.
Okay, like this plus an O?
O2.
2 plus O2?
Like that.
This would not be stable because actually this is impossible. It's impossible because there are 2 extra electrons, and those 2 extra electrons have to come from somewhere. If there's maybe a flame, it could be possible, because in a flame there are electrons, because a flame is an ionized gas, plasma, but this is impossible because the charge does not balance. This is a 0 charge, and this is -2, so we end up with 2 extra electrons from somewhere. We have to show that. If we did this, let's say 2 electrons plus an ozone, then we could get this. And then there are 2 negative charges. But since we don't have that, it's not possible. So we'd have to look for something else.
What about O plus, and then O2 minus, and then O plus?
O plus plus O2 minus plus O plus. Now that's possible because that maintains a charge balance. Because this adds up to 0, this is 0 here. But if there's a tug of war, between oxygens, which oxygen would win? Is it just, if you had a tug of war with your clone, who would be the winner? You or your clone? Well, you. Okay. Yeah, the original would win, of course. The original is going to be a little stronger and a little sharper. Right.
Not a photocopy.
No, right. Okay, the original. Which one of those oxygens is the original oxygen then? It must be this oxygen, must be the original.
Yeah.
True original, because this oxygen was able to pull an electron from this and this one. 2 of them. Does that seem very likely? No. I mean, can you even tell the difference between the oxygens? No, you can't. I mean, they could be different isotopes, but, different isotopes chemically are going to be similar. Although, the collisions will be different because the masses are different. So, is there anything else that looks somewhat reasonable on the list? Yeah, maybe this, an O2 and an O. Okay, we know ozone's very reactive. A lot more reactive than just O2. These are callotropes. Allotropes are different forms of same element. And so ozone is one allotrope, O2 is another. O2 is a lot more stable allotrope, oxygen. And so this looks reasonable, although it forms atomic oxygen. Atomic oxygen is very reactive because it wants to form bonds. What's that? It could react with whatever, another ozone or whatever else. And so atomic oxygen. So if there's going to be a violent collision, you know, you'd expect something like this. I mean, if something like this did form, it wouldn't last very long, you know. And so, you know, a violent collision probably would form something like this. You know, it depends on how violent. Maybe an extremely violent collision would form this, but the population of this, you know, product would be pretty low, you know, because it would need extremely violent collision because O double bond, you know, O double bond is fairly strong. You know, O single bond, you know, bond energies vary from about, you know, a couple of hundred kilojoules per mole to 1,000 kilojoules per mole for a covalent bond. And so, you know, we're looking, typical double bonds are like 600, you know, 700 kilojoules per mole, which is pretty high. So it's hard to break that double bond. Although, could happen, you know, possible. But which out of these, which one do you think is most likely? You know, yeah, the top one. This would have the lowest energy barrier. Therefore, it would be the most probable. All right. Does that answer your question? Jane?
Is the 14 test Tuesday or Thursday?
14 test. Do you want it to Tuesday, tomorrow, or Thursday?
Thursday.
All right, Thursday. Yeah, 14 test is going to be on Thursday.
Because I want Thursday because Raheem was behind on one workshop.
Okay. All right.
Just
Thursday. Oh, did you? Okay, that's fine. Do you guys have other questions?
You said there's a question on it. It says the rate constant depends on, there's 4 choices. We can circle the initial concentration.
Okay, when we're looking at the rate constant, we're just looking at K.
It depends on the initial concentration,
Okay.
the activation energy, time, and the frequency factor. I don't know.
The frequency factor is A. Is the frequency factor. Time or temperature?
It's a big T. Oh, it's by temperature.
Yeah, it's going to be temperature. Although time could be an option too. Well, K, you have to know the equation. You don't have to know the equation because I'm going to give you the equations. You don't have to memorize the equation.
Yay!
So one of the equations is this one. K is equal to A e to the minus EA over RT. And so here, it definitely depends on activation energy and temperature. This is the frequency factor here. The pre-exponential constant is called the frequency factor here.
How do you determine the frequency factor?
How do you determine, the way you determine this, how do you think you might determine the frequency factor for this? You know, what you do is you determine a lot of, if you determine one rate constant at a given temperature and you know the activation, but how would you get the activation energy? Well, this is what people do. In order to solve this, they rearrange this equation. And so they get the natural log of K is equal to, and then what we'll do is we'll take the property of logs and just add those and then move one to the front. And so we get minus EA over R, which is a constant, times 1 over T, which is a variable, plus ln of A. This is called a, you know what this equation's called? Arrhenius equation. What's the Arrhenius equation? This is what we call an Arrhenius plot, or what we want to make as an Arrhenius plot. If we look at an Arrhenius plot, if we just plot the ln of K versus 1 over the temperature, we generate an Arrhenius plot where the intercept will give us the frequency factor. So all we do is we just determine what the intercept is here, take the inverse natural log, and then we can get the frequency factor. And the slope here, we can get EA. And so we can get, we just need some data here so that we can make this plot. And that's how we can determine the frequency factor. That's experimentally. You can also try to determine the frequency factor theoretically, because the frequency factor is going to be related to maybe the probability of that. And so you just look at statistically, if you had a whole bunch of random collisions, what percentage of those collisions are in the correct orientation, right? Something like that. A high percentage of those collisions being in the correct orientation is going to give you a very fast rate, rate constant. Rate constant, is, bigger the rate constant, the faster the reaction is going to be. So it doesn't depend on the initial concentration, because the initial concentration is what we multiply K by to get the overall rate. Okay, other questions?
Yes.
Uh-huh.
On the decomposition of hydrogen iodized gas, it was like number 3, 2, 4, 6, 7, 8. Number 35. HI gas going to a half a mole hydrogen gas and a half a mole iodized gas.
Okay.
How to determine the order of the reaction? I thought it was first order.
How do you determine the order of the reaction?
Yeah, like when I did
Well,
it.
okay, what information did they give us? Because we don't know what the order is right now, because we don't know how many steps this happens in, And so all we can say is that the rate is equal to K times the HI concentration to the M power.
We have some data.
All right, what is the data?
At 0 seconds, the concentration of HI is 1 molar. At 100 seconds, the concentration of HI is 0.90 molar. And at 200 seconds, the HI concentration is 0.81 molar. At 300 seconds, HI is 0.74 molar. At 400 seconds, HI is 0.68 molar. Yep.
Okay, is that all the data that we have?
Yes. I tried plugging into the integrated rate law, but then I saw that the K was relatively constant for the first order, but the book says it was like actually second order.
Well, what we do is, since this is a homework problem, you could just graph this. In Excel.
When do we graph it and when do we not graph it?
You always graph it if you have, if you have that option. You just graph it. It's the quickest way of figuring it out. But you are not allowed graphing calculators on the test, right?
Yes.
And so what we do is we try to just analyze the data based on K analysis. Looking at the slope between the segments. And so for K analysis, this is a lot of points because, we get the K1 here, K2, K3, K4, and then, you could have things like this where, K5, and then K6, K7, etc. But we'll just look at the individual segments and C. But when we do the individual segments, we'll just pick the steepest and the smallest.
Wait, the steepest and the smallest?
Yeah, but you know, we don't have much time, so how many points do we need to define a curve? If you're pressed for time on an exam and you got a lot of data like this, then maybe what we'll do is we'll sacrifice a little bit of accuracy, or a little bit, we might, you know, risk random error screwing our calculation up. But, you know, what we might just do is we might just pick
These two rooms.
yeah, no, we'll just pick like ones that are farther apart. So maybe like here, we'll go with this segment here. We'll just call it KA. No, I shouldn't call it KA. Let's call it K.
K1.
K, whatever X. Yeah, that's fine. KZ.
They should have the same slope.
They should have the same slope. So we'll just do these two segments, and since they're far apart, then we'll, you know, because if we pick these ones that are close together, you know, ideally we do all of them because we'll get a much better K value that way. But you know, to do all of them is just going to take time. Since we don't have much time, we'll just do this, and so we'll pick this, the KX segment, and we'll just go 0. If it's 0, then we just take the final minus initial. Actually, you know, K is equal to the negative of the concentration final minus the concentration initial over the time segment. And so 0.81 molar minus 1.00 molar divided by the time. The time it took for this one is 200 seconds. 0.0095. Give me one more digit.
0.
0. Okay. This is going to be molar per second. Okay. That's for 0 order, and then we do KZ for 0, where it would be just
6.
yeah, just 0.68 minus 1.00. The time it took for that is 0 to 400 would be 400 seconds. What did that come out to?
Negative. Oh, it's a 0.0008.
800. So 800 and 950. That doesn't look so good. So it doesn't. It's not looking good for 0 order. So we go to what's next.
First.
Right. And we do repeat the whole process. You want me to go through it, or are you comfortable with it?
Yeah, just like the general procedure. Will be fine.
Well, for first order, K is equal to minus the ln of A times T over A initial divided by the time segment. We'll just set it up then. K is equal to negative the natural log of this first segment, which we're calling 0.81 over 1 over the time, which is 200 seconds. Then the second is KX, KZ would be negative ln 0.68 1.00 over 400 seconds. Is that your 99-cent calculator, John? It's still
hanging in
still alive? That's pretty good.
What happened, Joe?
Numbers.
John bought some calculators from the 99-cent store, scientific calculator for 99 cents. Which I bought before too, but it didn't last long. It lasted a couple of weeks and then died. But this new version, actually I picked one out. The new version is pretty good so far. So I didn't have a calculator for a long time. It won't solve the quadratic though.
Yeah.
But you know, at a $15 savings, maybe it's worth doing quadratic by hand. Depends, you know. well, anyway, you do this, and then what do? You take the percent difference, right? What's the percent difference here? What's the percent difference here? What's the percent difference here? We're only taking 2 points because we have multiple points there. And these are spread apart, but are not. So we really need 3 points. 2 slopes should be the same. Actually, maybe I shouldn't have done that. I shouldn't have taken this. Although, yeah, it'd be pretty clear. I mean, you know, the way I'm doing it is we're starting from the same point here and going here. So if it's linear, the second point lines up here. And so we take this slope versus this slope here. If it's non-linear, then this slope versus this slope is going to show a greater difference here. All right, is that okay, Kelly? We're figuring it out? Then we go to second order, second order. So I don't have my calculator. Second order, K is just equal to 1 over A times U over 1 over A initial over times and do the same thing, and then see what the percent difference. Ideally, we want 0% difference in the slopes. The slopes should match up here. This is for the concentration of A, versus time. But when we do the natural log plot, then first order should line up, and when we do the inverse concentration versus time plot, the slope should line up. All right, if you have time, then we want to get the K value. We want M and we want K. The K, you just average the two since this should be the same. But, the best is to get K1, K2, K3, and K4 and average them together. If you plot this up and do a linear least squares fit, then the slope is going to be the average K, so you don't have to do any extra work there. The trend line fit. Trend line fit's just going to average all your data.
Do we average our K values?
Yeah, it's just going to give you one slope. That would be the average.
I think she was saying that sometimes K comes out to be pretty close. For example, 38, the first order came out to be 0.0131, then 0.0126, 0.0117, which is pretty close. But then it turned out to be M2, but the K were a little.
Well, the thing is, if you calculate, what were the percent differences? Because did you calculate the percent
It
differences?
was closer to the.
Well, give me the number. What were the percent differences?
I didn't get it, but. Yeah,
See, the thing is, you have to calculate the percent difference. Give me those numbers, and let's calculate the percent difference, and then you'll see. Maybe they aren't as close as you might. I mean, looking at the numbers, eyeballing the numbers is difficult sometimes because it's tricky because the difference is different than the percent difference. It could be a large difference, but the numbers are big, so the percent difference comes out small. But anyway, give me those numbers.
0.0131.
0.0131.
0.0126. 0.0117.
117. And so if I look at this, this is about 20 out of 100. So this is roughly a 20% difference. Because from 111 to 131 is 20 parts out of 100. So 20 parts out of 100 is around 20%. So these aren't that close, actually. But let's go to the next series.
0.843.
0.843.
0.875.
875.
0.891.
891. And so if we look at this was about a 50. 50 out of 800. 50 out of 800 is about, well, let's divide that.
It's about 6.25% off.
6.25%, so this is about 6%. And do you see the difference? Even though the difference is much greater, it's 50, but the total number is much bigger. So it's very deceptive. This is why I always say you have to calculate the percent difference to show me, because some people just eyeball it and then go, well, these look very close. And they do. They look very close, but the percentages still a bigger percentage. Okay.
I'm having trouble with number 14.
Number 14? Okay,
Yes.
let's take a look at that. 14.
Because different the rate in terms of rate. This times R1, that times R1.
All right, just read out the question for number 14.
Okay, we have some data here. Initial A for experiment 1 is 1.40 and 1.40 and 1.00.
Okay, they give us a data table for number 14, or they give us initial rates?
Initial rate and the data table.
All right.
But the initial rate is not directly determined. It's written in terms of R1.
How many are there? How many reactants?
3 reactants,
A, B, and C?
yes, and 5 experiments.
And 5 experiments? Okay.
Oh, this is one of those manipulations.
And then what are the rates?
R1,
R1?
R2 equals half of R1,
Half times one.
R3 equals a quarter of R2, R4 is 16 times R3, and R5 is unknown.
All right. What did they do here?
1.40 on A and B, and 1.00 on C.
Just go down the list for A.
0.70, 0.70, 1.40, 0.70, 1.40, 0.70, 1.40, 0.70, 143. No, 1.00 3 times. And then the rest is 0.50. Okay, now there you go.
Compared to experiments at a time.
Yeah, we just compare to experiments. So actually this one, 1 and 2 would be easy because this is constant, so it only changes here. So what we do is we double here. So we double going from 2 to 1. What happened to the rate? The rate also doubled. You see that? And so we go up the double. So that means it's got to be first order in A.
Uh-huh.
And then we just look for where else can we get something.
It's like 2 and 3 is good for B.
2 and 3 is good for B. Okay. For 2 and 3, the difference is, okay, this is constant, but here we double. So 0.7 to 1.4. What happened here? It also doubled, so it's got to be first order in B.
I think it's 1 and 4.
Okay, 1 and 4?
I think that one works for C.
Yeah, 1 and 4 works for C. You see that? And so between 1 and 4, we double C. What happened to the rate? Well, 16R3, 16 would be 16 times 1/4 R2. This equals 16 times 1/4 R2. And so 16 times 1/4 gives us 4R2. Okay, R2 related to R1.
It's 1/2. Or 2 times.
R2 is 1/2 R1. So this is equal to 4 times 1/2 R1, which is just 2R1. And so this is 2R1, and we go to R1. So we double C in the rate. Does it double? 2R1 to 1/2R1, it goes 1/2, right? You see that? It went 1/2.
That's a negative one.
So yeah, it's got to be an inverse, -1 order. right? And so C's got to be a -1 order based on what happened with the concentration.
And overall, it's a first order.
Overall, it'd be first order. That is if I did the math correctly here. All right, this is just to get the orders, then we have to get the K values. To get the K values, we give...
We don't need. We need, what's the value of R5 in terms of R1?
Oh, that's all they want?
Yes.
Oh, then that shouldn't be hard to, I think. In terms of R1?
Yes.
All right.
I saw the book did a really rigorous calculation. I don't know
Well,
what's
now how about let's do this. We cut it in half. And then it's first order, so the rate should be cut in half. Right? We cut this in half, it's first order, therefore the rate should be cut in half. And then over here, we cut this in half. If we cut this in half, then it's 1/2 to the -1, which is 2. And so we just multiply these together times R1. So it'd be 1/2 times 1/2 times 2 times R1, which is equal to,
2 R1.
no, 2 R1, to 1/2 R1. Because, you know, this 1/2 and that 2 will cancel. It gives us 1/2 extra. So it should be 1/2 R1. Okay.
1/2 R1.
Does that make sense? If I did everything right, it should be 1/2 R1.
Okay.
All right, other questions?
Yes.
All right, well, I'm going to bring up this book. Go ahead.
Okay, wait, but before, in the book it says it's 1/4.
It says it's 1/4 R1. Then I probably made a mistake. Did I make a mistake?
Yeah.
16 R3. R3 is 1/4. That's 4 R2.
Well, because in the book it says B is in the second order, so maybe that's.
B is second order? I think B is second order.
It's weird. So,
Okay, so this stays the same, this stays the same. We double, going from 3 to 2, we double. Oh, you know what?
The
We
rate is
doubled
still in-
this. And, oh, this, you know why? I looked, I didn't, this is R1, this is R2, they're different.
yeah.
That's where I screwed it up. It looks like it doubled here, going from 1/4 to 1/2, but this is R2, that's R1. So I made a mistake there. And so we have to get this in terms of R1. And so R2 is equal to 1/2 R1. And so this is actually equal to 1/4 times 1/2 R1.
It's 1/4 R2, so it's 1/4.
And so that should be 1/8 R1. And so we're going from 1/8 R1 to 1/2 R1. So this is wrong. It should be times 4, which would make that, if we double this and this increase 4-fold, it's got to be second order. So I screwed that up. And that means this is wrong here because this is going to be 1/2 to the second order, not 1/2 to the first order. And so that would be, well, 1/2 to the second order is going to be 1/4 R1. That would be correct.
But that wasn't the question is on the practice exam, for
Mhm.
number 15, it says, in the rate law, A, A to the N, B to the N, for the reaction A plus 3B equals G, where does M and N originate from?
Mm-hmm.
I have no idea.
Number 15.
Yes.
I'll just bring that up.
But you're not gonna ask those acid questions, right?
No. We're gonna do the acid lab tomorrow. Actually,
Wait, what acid lab?
oh, you know. What acid lab? A Spartan acid lab. All right, thanks to James for posting this.
Huh?
I think it's under the, will there be a chapter 14, that one, and then on the bottoms, yeah.
Which one was it? The B or the C?
14C.
14C. All right, number 15. What was it?
Oh,
What number?
actually, sorry, it was 14B. Yes, at the bottom.
Okay, in the rate law, for the reaction, A plus 3B yields G. Where does M and N originate from?
The coefficients.
Yeah. Yeah, well, I'm saying originate. I'm not saying how do you derive them or how do you figure them out. Where do they come from? Theoretically, where does M and N come from? The origin of M and N. Theoretically. The mechanism, the slowest step of the mechanism. It's the molecularity. The molecularity is, what molecules of species are involved in the collision of the slowest step of the mechanism.
I had a question that, how do you know that for elementary reactions, the coefficients are the exponent?
How do you know? Well, it's just a simple collision. So, physically, it has to be that way because if you have a simple collision, A plus B, if you double A, you're going to get twice as many collisions. If you get twice as many collisions, then you'll have twice as much reaction. And so it's going to be first order in A, right? The same thing with B. If you double B, you're going to have twice as many collisions with B, which means it's going to be first order B. Now, if you have an A plus an A, then you double A, well, it's going to double both sides. It's going to double the left side and the right side, resulting in a fourfold increase in the number of collisions. So it's just based on the physical collisions that you have, and you know that, there's no hidden steps in here. And so this is it. And so it's got to be based on the, physics of collisions or just based on counting collisions. It's got to be the coefficients, because here it's going to be 2A, and it's going to be second order in A,
That's because they tell you that there's no other reaction.
Oh, okay. How do you know it's an elementary step? You don't know. You have no idea. I don't know if that's elementary or multi-step. And so you have to be told that, or you make an assumption. You just say, let's assume that's an elementary step, and then this would be the rate law. Otherwise, you can't guess. Now, this is most likely not an elementary step because this would involve a 4-molecule collision. And coordinating 4-molecule collision with enough energy in the right orientation would be low probability. And so most likely, this is a multi-step reaction. I mean, it'd be very weird if it were a single step. Termolecular, 3 molecules might happen, that's possible. In the homework, there's one termolecular elementary process that occurs.
As far as knowing which one's the slow or fast, you're also told?
You're also told, or you guess.
Yeah.
You guess, yeah. You guess and see if it works. Guess and check, that's all. Or you're told, I did a combination of both. So the book tells you the mechanisms and shows you the derivation. We went from the rate law to try to derive the mechanism. So this is why we're just guessing what the products of certain reactions are. And so where does M and N originate from? They originate from the slowest step of the mechanism. That's where they come from. Maybe not directly. We might have to do the fast reversible, that kind of thing, maybe more than once to get it eventually. This is the molecularity. M and N are the molecularity for the original reactants, how they're going to impact the intermediates in the particular mechanism. Okay. how that depends. And so it's not necessarily first order in A and third order in B, you know. All right, other questions?
Go over at 10:42, 14C, the like graph intersection.
The 10, this thing?
Yeah.
1014. This is called a reaction coordinate diagram or reaction progress diagram. So it's just spreading out an energy level diagram. You know,
Which one's the fastest step?
which one is the fastest step?
Yeah.
Yeah, which hill would be the fastest to climb over if you're on a bicycle? Which one would it be? B to C. B to C would be the easiest hill to climb on a bicycle, right? So that should be the fastest step because most people will get through that quickly. Let's say you have a whole big group of riders, you know, and most of them will be able to pass through B, C more quickly. Which is the slowest step? You know, the highest activation energy. And is it CD is the highest or AB? AB, because you'd measure it from the start, you know, A here to the top.
You gotta get over that big huge snowstorm.
But C, you just measure from the start of the hill, right here to the top. And so you just kind of eyeball it and see. A to the top would be a bigger climb. It's not A going to B because this is a climb up here. It's A to the very peak of the hill and C to the very peak of the hill. And so the highest activation energy would be the slowest, and that would be A to B. How many intermediates are there? 2. Yeah, B and C would be intermediate products before getting to the final product, B. How many transition states are there?
Count the number
Yeah,
of feet.
three transition states. You know, at the top here, there's got to be some transition states showing the bond breakage and formation here and here. So 3 transition states. Is the overall reaction endothermic or exothermic? It'd be endothermic, yeah.
Positive on the
Yeah, delta A, actually this is potential energy. So what would that be? Well, this is potential energy, which we call PE, all that. We should, you know, typically we'll have enthalpy or something like that. But delta H would be like this, A to B.
We're pointing upward.
Pointing up.
What if you can't tell that the reaction is exothermic or endothermic? Like the arrows are pretty close to each other.
Then just describe.
If you can't tell, then you just say there's no change in energy.
Or almost no change.
Like for
Almost
this
no
one right
change.
here, number 49, I can't tell whether it's exothermic or endo.
All right, let's take a look at that one then.
Oh, it's definitely that.
Didn't I just sign into this? I guess not.
If you look at how far A is from the bottom line compared to D, there's a big difference.
You're saying it's exothermic then? What number was that, 12?
49.
49, so. Let's take a look at that. Oh, this you just, what you do is you just draw a horizontal line here
Aha.
where A is, and A ends up about here, and D's below it, so it's got to be exothermic.
Small exothermic, but definitely exothermic.
Definitely exothermic. Now, if they're at the same level, you know, if you drew a line from A and it superimposes with D, then you just say delta H is 0. What is, are they doing potential energy again?
much the same question. We just looked at it on the test.
Yeah, all right. So this would be exothermic. It could be that the change in potential energy is zero, you know, the same energy level. But this one's clearly exothermic, even though it's not very exothermic. There's not a big change in energy there.
Which one's the fastest step? I believe it's B to C.
Smallest number. C.
This
C
is
to D a little
tricky
smaller.
because B and C almost look the same.
I'd say C is a little smaller.
Is C a little smaller?
I think so.
Yeah, you know, you'd have to get a pencil and maybe a ruler and measure it, and then just see which one's the smaller one. You know, it's between B and C, BC to CD. I don't know. You're saying CD is smaller?
Yeah.
Okay, CD. CD looks smaller because it looks like they're, you know, this is called the line width, how wide the line is. This is a much thicker line width than that. Something like that. Okay. So what else?
Are you gonna have to memorize the equations, or are you gonna provide us?
No, you don't have to memorize any of the equations. I'm not going to tell you what they are or how to use them,
So you're gonna,
but I'll provide you with the equations. All the integrated rate laws, you don't have to memorize any of those. There's certain equations that you might, you know, have to derive. I didn't do this because in an effort to save time, I eliminated some stuff out of my usual thing. But usually, like these types of things, there's certain equations that might be useful, like the T1/2 equations. You know, T1/2 is, you know, the time it takes to go from initial to 1/2 initial. And so, you know, for first order, okay, if we go to 1/2 initial, so that's 1/2 initial over the initial over T1/2, you know, this is what K is equal to. Actually, we're solving for T1/2, so we'll say T1/2 is K over here. And so, what's the natural log of 1/2? You know, yeah, and so T1/2 comes out to 0.693 over K. You know, an equation like this is given in the book. I forgot what equation that is, but I probably wouldn't give that to you because it's a pretty straightforward derivation.
Dude, that's really
Hmm?
Yeah, the 693 is because the concentrations cancel out, so you're left with a.
Well, the same thing, you could do like 99% reaction. So, you know, T at 99% reaction, it would be the time interval for, okay, the concentration at time T, or 99% reaction, is equal to 0.01, the initial, right? And so if we want 99% reaction, then it's just, it's this first order I'm saying, then at time 99%, we have 0.01 remaining of our initial over our initial. And so we could do the same thing, you know, but we aren't gonna generate an equation for each, right? We aren't gonna generate an equation for 50% reaction, 99%. I mean, we might generate an equation for 50%, only for first order, because first order have a constant half-life. But for second order, you know, I told you the half-life doubles, right? And for zero order, the half-life gets cut in half. We could derive that equation. So if this were zero order, we go T equals blank for, you know, the concentration time T equals half of the concentration initial. And so when we do zero order, okay, so concentration at time T is 0.5, the initial, minus the initial, divided by K. This is going to, well, what does that give us? This gives us 0.5 times the initial divided by K, which is 0.5 is just 1/2 over K. So, if we cut down the concentration each time, the half-life gets cut in half. Whereas for second order, it'll double because it's inverted. It doubles, and we end up in an equation where it's 2 times the initial. Okay? But you see here in zero order, the concentration doesn't cancel out. We have concentration there. So zero order and in second order, the concentration, it depends on the concentration.
You would give us the integrated rate law for us to.
I would give you the integrated rate law for you to do that. You would just have to plug those in.
Oh, and one more on the exam. It says catalysts speed up reactions by lowering aggregation energy. That should be false, right? They just provide alternate. Like which in turn lower energy.
I think it does.
Which one is that? Number 5?
8.
Number 8?
Yeah.
This is actually 8 is true.
8 is true? Okay.
Yeah, because providing a different mechanism with lower activation energies is the whole point of catalyst.
It's page 639.
Yeah, you want to lower the activation energy.
I thought it would be like a trick question. You know, like wording it.
Well, you know, the enzyme's pulling apart on the substrate molecule, so trying to, weaken that bond so it's easier to break.
Because there's a question like that on the homework that tells you that it's not really worded right if you say it like that.
Okay, what question is that?
It's 59, I think, or yeah, 59.
Where are you on? Homework anyway.
But not stated as carefully as they might be.
The following statements about catalysts are not stated as carefully as they might be, and I can't scroll down more than this because something's wrong. I don't know, this is so
There you
weird.
go. See if you read it. The deal is
What slight modifications would you make in them? A catalyst is a substance that speeds up a chemical reaction. That's true, right? Speeds up a chemical reaction, but does not take part in the reaction. That's false. That's false because the catalyst is consumed initially and then spit out again. And so catalyst does take part. It's not. I guess you could say it's just cycled through the reaction, but it comes out whole again. So it's not actually consumed, but it takes part in the reaction. So therefore, if you had no catalyst, you wouldn't have any reaction. What?
or it'd be a lot slower. Or no reaction period.
Yeah, so here, when we did the acid catalyzed decomposition of formic acid, the first thing is, right, one of these oxygens attacked the acid. We had that. Turns out this one. We call these oxygens different. We call this oxygen a terminal oxygen, because it just ends there. This oxygen is called a bridging oxygen. Terminal oxygen is sp2, bridging oxygen is sp3. So this bridging oxygen attacks that. Although the terminal could have, but we saw that was a dead end. And then we end up with this, but in the end, it's spit out again. And so we definitely need the catalyst. And the reaction rate is going to depend on how much catalyst you have. If you don't have enough catalyst, it's going to go a lot slower. If you have plentiful catalyst, it should go a lot faster. So it's going to depend. I mean, this will depend on this will be first order, I think, the catalyst. So we double the catalyst, we should double the rate of reaction. And so in that sense, the catalyst does participate, but in the end, we start off with 1 molar H+, we're going to end up with 1 molar H+. It's just going to be the same.
So let's talk about part B of that. It says the function of the catalyst is to lower the activation energy for a chemical reaction.
Yes,
This
that
is
is
all I know is
true.
comparing it.
Oh, I see what you're saying now.
Yeah.
The function of a catalyst is to lower the activation energy for a chemical reaction. That's true.
Yeah.
But yeah, the way that they changed it was.
How do they change it?
To provide a different energy path. That doesn't necessarily lower. But yeah.
Well, the whole point of having a catalyst is to lower the activation energy. And so, if you're trying to design a catalyst, how are you going to design the catalyst? Well, you want to try to design the catalyst to provide an alternate mechanism that lowers the energy path. Because if you have an alternate mechanism that increases, let's say if I have an alternate mechanism that actually increases, this is going to go slower.
Question is,
But, you know,
those
not-
three little hooks add up to the size of that one big.
No, no, they don't, because they're taking one step at a time. You don't, yeah, these three humps, you're thinking about like the total energy expenditure, but no, it's not like that. It's not like there's a limited number of calories that these have, you know, because we're dealing with thermal energy. The temperature is going to be, there's going to be a certain percentage of collisions, so it doesn't matter. We're just looking at these individually. And so the biggest hump here is a heck of a lot smaller than this. Therefore, this is going to have a much higher probability, because essentially what that does is, if you look at the Maxwell-Boltzmann distribution, without catalyst, with catalyst, here. And so what we do is lower that activation energy, and then the population dramatically increases. And then we're going to have a much faster rate, right? A population of molecules with enough energy to react. Yeah.
Okay, why are there two activation energies?
They're not two. How many activation energies are there?
Three.
Count them. 3. 1, 2, 3. There are 3 activation energies here. Why?
2 intermediary steps.
Because there must be 3 steps. If there are 3 activation energies, there must be 3 steps in this mechanism.
So you're not gonna be that particular about your answer?
No.
Okay.
You don't have to tell me why there are 3 steps in the mechanism. You know, it's just, that's what's observed. There are 3 steps. So just take it as given. All right, any other questions?
Is it possible to do number 16 together on the back decision?
Is that homework or is that test?
B?
Yes. No, C.
C?
Yes, that one.
All right. Propose a 2-step mechanism. Step 2 is the RDS, which stands for what? Rate determining step, the slow step. For ozone decomposition, derive the rate law using the steady state approximation. And so 2 steps. So we have, we only have 2 molecules here. And so our choices are unimolecular or bimolecular. Those are our choices.
So it doesn't hit a wall or another molecule.
Right, and so bimolecular sounds pretty good, right? We could go with bimolecular. And so an ozone plus an ozone. And then we have to figure out what could be produced when an ozone collides with an ozone. Although you might go, this question sounds vaguely familiar with number 5, right? And so if you go back to number 5, I would have started with bimolecular, but when I look at number 5, when ozone undergoes a unimolecular collision, the most likely products are. So maybe that's a clue for, maybe we should go with unimolecular first. So let's try unimolecular.
It's a distractor as you're flying.
And so out of these options here, which one do you think looks the most?
D.
D.
Because of charge balance.
Yeah, charge balance. And D would require less energy than B. And E, this charge balance creates a huge voltage, which, if you're thinking about static electricity, this is going to be very unstable. Look at those. Remember formal charges. High formal charge is no good.
Yeah.
When you get to +2 formal charges or +3 formal charges, it's very, very unstable. And so E is not so good, and C, definitely, C is impossible, A is impossible. And so B, D, and E are the options, and out of those three options, it looks like the D. Okay, so we're gonna call this one fast, right? Fast and reversal is usually what we do. All right, so let's just start with a unimolecular and see where that takes us. And it turns out that this is what we call an intermediate, and we have to get rid of that. And so we can get rid of that by applying an O3, which is going to give us two O2s. And so if we use this as a two-stepper here, then we're going to get the intermediate cancel out, so it'll be ozone plus an ozone yields 3 O2s. And so that's what we want. Ozone, 2 ozones yields 3 O2s. So the net reaction is okay. And then we're treating this one as a slow step here. And so we're going to label these K1, K minus 1, K2.
Excuse me, how do you know O plus O3 gives you 2 O2s?
Well, we could try different options, just like this. O plus O3 might give us an O2 minus, an O2 minus, and an O2 minus. Oxygen likes a 2 negative charge, so how does that look to you?
Good.
This looks impossible.
Looks like you're missing an O.
I'm missing 6 electrons. Where are those 6 electrons coming from? Because the oxidation states are 0 and 0 and 0. The electrons aren't coming from anywhere. This is impossible. But then you go, okay, I'll have an O minus 2 plus an O plus 2 plus an O. And then you think, if there's a tug of war for electrons with one oxygen, you know, it depends. If there's a super violent collision, you know, this could happen, but how stable these, this is going to be highly unstable. Okay, but maybe let's lower the charge. O minus, O plus, and O. You know, because remember electron affinity, EA1 for oxygen is actually exothermic, so that's good. EA2.
Sorry to interrupt. Isn't there 4 oxygens on the left and 3 on the right?
Oh,
Excuse me?
yeah.
Okay, I just want to make sure I wasn't missing something.
No, you're right. I was thinking ozone, but actually there are 4, right?
No matter what, it's not looking good.
That's charge balance. There, right?
This is better. This seems to be better because I have to do EA1. This is going to be EA1 plus EA2, which is EA1 plus EA2 for oxygen is net endothermic. This is exothermic, so this might happen. This is going to be highly endothermic, IE1. This is going to be an IE1 for this. This is going to be EA1. And so maybe that might work out because EA1 is exo, and IE1 is endo, so maybe it balances out. Let's just take a look. Do you guys remember any of the numbers off the top of your head? EAs? EAs are, you know, not that big in the hundreds, whereas IEs are big in the thousands of joules, right? Thousands of joules. You should have some kind of reference point, you know, remembered for some of these numbers. In other words, you shouldn't ignore the magnitude of the numbers completely. But maybe this is a good time to go back and take a look quickly at
10 or 11?
what chapter was that? 9? 9.
Which chapter was it?
9.
Ooh. Damn, that's a wild looking graph.
Well, we don't have the table here. Oxygen's in there, but I don't think I can scroll down, but we can figure out oxygen's around here, right? Oxygen,
Yeah,
fluorine,
oxygen.
neon. So it's going to be around here, about 1700, 1800 kilojoules per mole. Right? So it's pretty high. Oh, okay, we don't have oxygen. Oxygen's in the homework. I could dig it out, but I don't want to dig it out. I just want to look at the EAs next. Let's look at the EA. So remember that number, 1700. EA1 for oxygen is minus 141. 17 plus 1700, so this is going to be about plus 3400 kilojoules minus about 200, 300. It's not even close.
Dang.
Right, that's going to be highly energetic, right? It's going to be highly unfavorable. And so this is the tug of war we're talking about, but if you want to use Hess's law, you can and figure it out, because you can figure out the delta H's of these things individually just to look and see. You know, that's the delta H, but then there's going to be collision transferring those. Anyway, let's go on to other possibilities. What other possibilities are there?
That was a 202.
We can have an O2.
Okay, 202.
No, only one. Wait, one
All right.
O2.
102 plus an O plus an O. How about that?
Might be good.
All right. Or maybe we have an O plus an O plus an O plus an O. These are all neutral. That can happen. Yeah. And so what we do is we try to figure out, well, if you have an atomic oxygen and another atomic oxygen, what do you think they're going to want to do?
That's so nice.
If they come close to each other, what do you think they're going to do? They're going to combine. Is it, when you're breathing the air in here, are you breathing atomic oxygen or are you breathing diatomic, molecular oxygen?
Molecular.
Why? Why are you breathing atomic oxygen? Because molecular oxygen is more stable, and if there was any atomic oxygen, that atomic oxygen would immediately be converted into molecular oxygen because it's a heck of a lot more stable. And it's a heck of a lot more stable because it's got a double bond, right? And these are called dangling bonds because, you know, they got some electrons here, two dangling bonds. This wants to form two more bonds or get two more electrons some way.
Twice as likely to grab
And so both of these have dangling, if they just come together, those dangling bonds can be a bond, you know? They're double bond. And then we're good. And so atomic oxygen, this is unstable. You'd expect if two atomic oxygens came together, they would form diatomic oxygen or O2. And so this is why we came up with O2 plus O2. It was the only sensible one option that we had. And so this is just trial and error. You know, this is just a guess, you know, you just try to guess what the products are. Of course, it helps to have some experience doing this. So this is why we went through some of these to try to gain some experience doing this.
I just barely finished the homework, so I am only today to review.
Okay, yeah, if you finish it, then you can go back through it a few times before the test. That's always very helpful. Okay, any other questions on chapter 14? None? We got 15 minutes or so.
So it's just trial and error and charge.
Well, no, it's trial and error to guess, but then you have to use some understanding of bonding and other things like, you know, electron affinities, ionization, or, you know, you don't have to understand this ionization, electron affinity. You just think of this in terms of a tug of war. Electron affinity is the pulling power of this, or one side of the equation, and then you have the ionization energy on the other. You know, it's just, or in terms of the tug of war analogy, this just doesn't, this looks very bad.
I've never seen that in chemistry.
You know, if you had two identical twins, truly identical, just, you know, well, maybe I shouldn't say identical because the environmental factor in addition to the genetic. But you have two identical species, which one's going to be more powerful? Two identical species. Which one's more powerful?
CO2 minus will be.
Well, I mean,
Neither one.
oxygen has electronegativity of 3.5. Oxygen, we're going to use all these Chem 1A tricks to try to figure out what's going to happen. This oxygen has 6 electrons. This oxygen has 6 electrons. This oxygen comes in at 3.5, this oxygen comes in at 3.5, and now they're going to battle or have a tug of war for their electrons. Which one wins?
Neither one.
There's a tie, right? If there's a tie, we call that a double bond, a covalent bond where they share them equally. You wouldn't expect an ionic bond, now would you? No. Well, I don't know if you'd expect it or not, but and so this is the additional information that we've used to figure it out. A non-polar covalent bond. Anyway, what's next? Well, what's next? If there are no other questions, we're going to go on to chapter 19, back to that, and see. This is what we have for delta G. Now, this can just tell us our driving force. Now, for delta G, we can change the driving force. And so the first thing we look at is temperature and delta G under standard conditions. And so here we see that delta G naught at some temperature is going to equal delta H naught at that temperature minus T delta S naught at that temperature. And then we can make this assumption that delta H and delta T don't change much with temperature. And so we'll just say delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. As long as they're in the same phase. As long as the phase doesn't change. You know what the phase is, right? What is the phase?
Solid.
Yeah, solid, liquid, or gas. As long as the phase does not change, then delta H and delta S do not change much with temperature. So let's tell temperature and delta G standard. And then this is driving force under standard conditions and temperature. So we can change that, you know, increase this, decrease that. That's going to change delta G naught. Now, if we go non-standard conditions, non-standard conditions at 298 Kelvin. Well, what if we don't? Well, then, you know what? If we're under non-standard conditions at 298, then, you know, delta G under non-standard conditions is equal to delta H minus T delta S. And so this would be at 298. This would be at 298 Kelvin. This would be at 298 Kelvin here. But we need the non-standard, you know. And then at some generic temperature T, then we need delta G at that temperature T under non-standard conditions is equal to delta H under non-standard conditions at bed temperature minus T delta S, non-standard. And what we'll just say is the same thing. This is going to be about delta H under non-standard conditions at 298 minus T delta S, non-standard conditions. But we rarely calculate it like this because we don't usually have this, you know. This data, do we find this in Appendix B? That is delta H and delta S under non-standard conditions is not equal to delta H and delta S under standard conditions. We can't just go ahead and say, okay, you know, under non-standard conditions, the delta H and the delta S are going to be about the same. They're going to be different. And so unfortunately, unlike this, you know, if we keep it under standard conditions, this is why I emphasize, you know, you got to understand what standard, a lot of people don't even know the definition of standard thermodynamic conditions. And they go through the entire chapter without knowing what the definition of standard thermodynamic conditions is, but you know, they're really hurting themselves for future understanding. But anyway, we got to keep track of this. In thermodynamics, we always have to keep track of all these things, because if you try to apply standard conditions and you're dealing with non-standard conditions, the equation's going to fail, your calculation's going to fail. But nobody's going to tell you that, right? Until you see, you know, that you got the answer wrong. That happened. And so we don't usually do this. We don't have this data. We don't have this data here. You know, so what we do is, the most common thing we do is we apply a correction. And so we apply a correction to it. So if we're looking at delta G under non-standard conditions, we'll just take our delta G under standard conditions and apply a correction. And the correction, we can look, you can go back and you can take a look in your book for the derivation, or we can look at the derivation really quick for this under non-standard, but we don't have to really worry too much about the derivation. You know, it's just some math. Let's see. Gibbs energy change. Well, here's how the temperature is going to impact. You know, our delta G might be negative at low temperature and positive at high temperature, or negative at high temperature, positive, or there might not be change. It might not go through the zero. But you know, the delta G is always going to be changing. It might not change sign, but the delta G is always changing. Now, when we look at under non-standard conditions, we can go through a derivation like this here, shown on page 839. And as we go through this derivation, we're going to come up with this equation here. And this equation is going to be this one, 1912. That is delta G. We apply correction. And so we're looking at the standard conditions. And R is just our gas constant, thermodynamic gas constant. Q is, you know, the activities, G. Activities, G, G, H, H, dot, dot, dot. These are the initial, or whatever you're given, AA, PB, dot, dot, dot. And so Q is the reaction quotient. Reaction quotient. Delta G's are standard. And so, you know, our standard, what does standard mean? Standard means that the concentrations are all one molar, and that the pressures are all 1 atmosphere, or, you know, it depends if we want to do US or SI, international. So that's what we get. However, Q, you know, Q is just whatever you're given. The concentrations need not be that. Okay, and so we can apply this this correction. And let's just do a calculation with this. And so let's take something that we know what it is. So the example would be like H2O. H2O liquid goes to H2O gas. If we do delta G under standard conditions, what is delta G under standard conditions for this? We have two ways of calculating. The common is delta H naught minus T delta S naught. That's one way. But we could also use a Hess's law variant for this. It turns out, Hess's law variant is we can sum up the delta G's of formation. And just like in delta H's, if we sum up the delta G's of formation for the products minus the sum of the delta G's of formation of the reactants, this gives us another way of determining delta. And so it depends on which one's easier to do. But they both should give us the same answer. So let's do it both ways. This is going to be under standard conditions. And so we go to Appendix D and take a look at the data there. I should just memorize the page for this one. So we're in hydrogen. So this H, here we are. All right, so the first thing we'll do is we'll do it the top way. Let's just go ahead and calculate what is delta H naught for this reaction. This is going to be delta H naught at 298 Kelvin. And so we're H2O, we're going from H2O liquid to gas. So gas is final, minus 241.8. I'm not going to write out the equation. It's 1 mole, it's minus 241.8 kilojoules per mole, so it'll just be minus 241.8. So that's the products, delta H of formation of the products minus the delta H of formation for the reactants. So it's a minus 285.8. And so minus 285.8, and this comes out to 44.0 kilojoules.
What does that mean?
That's delta H for this.
Like, what does that number mean? Is it like positive, negative?
Right. Okay, this is what it means. If you draw out the enthalpy diagram, then we'll have H2O liquid at lower energy than H2O gas. And the enthalpy difference between these two is plus 44.0 kilojoules. And so H2O gas, 1 mole of H2O gas under standard conditions is less stable than 1 mole of H2O liquid at 298 Kelvin.
It requires energy, so it's endothermic.
It's endothermic. That's what it is. What about the entropy? This is not favorable, right? Endothermic. Well, let's take a look at the entropy. Entropy is absolute entropy, so we'll just take it. It'll be the entropy final, which is 180.8, minus entropy initial, 69.91. So 188.8. I'm not writing out the equation to save time. Minus 69.91. The units are different here. This is joules per Kelvin mole. We have 1 mole. And so the entropy change is going to be 100 and, is it 113? 119? 118 point? 118.89. Joules per Kelvin. All right, we're almost out of time here, but we can just plug in the this in here. So delta G naught at 298 Kelvin is going to equal delta H 44.0 kilojoules minus T, which is 298 Kelvin, times this 118.89 joules per Kelvin Kelvin cancels, but the joules and kilojoules don't. So let's convert this into kilojoules by dividing by 1,000 joules. And then we're going to see that this comes out to, let's just finish this one calculation. What does it come out to? 85 point, huh? 35.39, positive 35.39 kilojoules, which means it's non-spontaneous. So does water spontaneously convert into? It's negative?
So that means more disorder.
It's negative?
Right.
Then I made a mistake. I gotta figure out where my mistake was.
So what does that negative mean? Is it spontaneous or not spontaneous?
I thought it was.
No, it's not negative.
No, it's not, it's 9 kilojoules.
It's 9 kilojoules? Okay. Positive 9 kilojoules? Okay. All right, we'll continue this next time. It should be non-spontaneous.